Hey guys, welcome back. In the previous session, we did a deep dive into the fundamentals of Docker containers, including C groups and namespaces. Now, in this session, we will be covering the next important concept of Docker internals, that is the Docker storage driver. Now, it seems that building an isolated runtime environment or containers just solves part of the problem. Without Docker storage drivers, launching containers would be so slow and inefficient that it would have been unfeasible to use Docker at the scale we see today. Docker storage drivers are without a doubt one of the main reasons for its success as a containerization technology. Now, to launch any application inside a container, you do require a long list of OS libraries and dependencies. Now, ideally, you will be required to make a separate copy of all those libraries for each of the containerized process that you launch. Now, this process is not only highly inefficient but also unfeasible, as launching containers will take so much time that people will see no advantages in switching to Docker over traditional virtual machines. Now, the Docker storage driver basically figured out a way to avoid making these full copies using mechanisms like copy on write and union file systems. Now, the idea of copy on write is not new, which is also sometimes referred to as implicit sharing and shadowing, and has been historically used as a resource management technique. This technique is heavily used in RAM resource management and is also used in some storage and snapshotting technologies. Now, Docker uses this technique to solve the problem in hand, that is, to devise a mechanism to effectively share files and libraries among containers. Now, during the initial days of its development, when Docker was still called .cloud, the Docker development team were on a continuous lookout for a copy and write system that will fit their requirement. Now, I believe UFS, or the Advanced Union File System, was the first copy and write storage driver to be used to build Docker containers. However, at that time, none of the mainline Linux kernels inherently supported any copy and write functionalities, and hence this had to be externally patched and managed by the Docker team, which was a bit of a tedious and messy procedure. However, once Docker grew and its popularity increased, the Linux distributions acknowledged the importance of integrating Docker with their OS, and hence started to contribute and develop copy and write functionalities into the Linux kernel. Now, over time, many copy and write storage drivers were developed and supported by Docker, namely the UFS, or the Advanced Union File System, BetterFS, Device Mapper, that is also used in LVMs, OverlayFS and ZFS. These storage drivers can mainly be categorized based on whether they operate at the file level or at the block level, as you can see in this chart. Now, the default storage driver today for Red Hat and CentOS 7 systems is the Overlay2, as you can see here in the output of Docker info, which is what we will be covering in this session. Now, the OverlayFS is the modern version of the Union file system. The diagram shown here is a great visualization to help you understand how Union file systems work. Now, in Union file systems, there is a layered approach to storing files and directories, again, which are still basically stored on your native OS file systems like XFS. However, the job of Union file systems is to create a merged view from the top where it cumulates all the underlying layers into one unified view. OverlayFS is also a type of UFS, or Unified File System, and involves individual files and directories as branches or layers. It then allows a virtual merge of these layers to provide a unified view. Remember that these underlying layers can be on different volumes or even different file systems. Now, I understand that at this moment you all will be having a lot of questions. The first one being, what is the use of such an approach? Well, don't worry, things will start to get clearer as I show you all some of the practicals. For now, just know that this layered approach is essential as it allows us to share the layers across containers. Now, before we move ahead, I want to introduce one more important topic in Docker, that is the Docker image. A Docker image is nothing but a reference to the union of one or more read-only layers. A Docker image is essentially built using line-by-line instructions where each line is actually an instruction on how to build a layer. Now, Docker provides us a tool to build these images called Dockerfile, which we will see in a few moments. Dockerfile is basically a text that contains the line-by-line layer creation instructions. Now, before I move on to my Linux terminal, I want to show the Docker Hub, which is a cloud-based Docker image repository. This is used by the Docker community to create, test, and distribute container images. Here you will find Docker images for almost all well-known Linux distributions and applications. Now by default, Docker will automatically try to download all images from the Docker Hub over internet if not available locally. Here I have a fresh CentOS 7 installation where I have installed and started the Docker daemon. Currently I do not have any Docker images available, which you can see from the docker image ls command. Now I will download the official CentOS 7 Docker image from the Docker Hub. The command for which is docker image pull, the image name and the tag. Now Docker image tags can be thought as a type of versioning technique for Docker images. Every image that you create by default will be assigned the tag latest. However, you can put your own tags to convey useful information about that particular version of the image to your users. You can see here the list of tags or versions of the CentOS image available for download. Now I have downloaded the CentOS 7 image and I can confirm that using the docker image ls command. On a side note, Docker CLI commands usually follow a basic syntax of the keyword Docker followed by the Docker component, options, and then the command or the action to be performed along with its arguments. By Docker components, I mean the basic building blocks of your Docker environment, that is Docker images, containers, volumes, network, etc. You can always see the list of actions available for a component using the help option. Here I use the help option for Docker image. Similarly, the Docker network, and so on. Now that we have downloaded a base CentOS 7 image, I'm going to build my own customized Docker image on top of it. Before I do that, I want to show how Docker has created our base layer in the backend for the image that we just downloaded. For this, I will go to the directory /var/lib/docker, which is the default Docker storage directory. Now remember, you are not supposed to ever directly interact with this directory. Never try to change or update any file under this directory as it is fully managed by Docker, or else you risk corrupting your Docker environment. Now I only moved to this directory because I want to show you all what happens behind scenes in Docker which you do not see normally when dealing with Docker containers. Now here I will move into the Overlay2 directory. Here you will find a directory for each overlay layer that is created. Layers are identified by applying a hash algorithm to their contents and hence the long weird name. Now this layer is the one that was created with the CentOS 7 image that we just downloaded. If I move into this directory, you will see a directory named diff and a file called link. The link file is nothing but contains a shortened symbolic link identifier for that layer. This shortened identifier is just to avoid any long name limitations with the mount option. The important thing here is the diff directory, which consists of all the files and directories that are part of that overlay layer, which in this case is all the CentOS 7 libraries and directories. Now the name diff will start making more sense when we create a new image layer. To create our own Docker images, we will be using the Dockerfile. In simple terms, a Dockerfile is just a text file that contains a list of instructions on how to build a Docker image. As mentioned earlier, these instructions are written in a layered format where each line of the instruction is converted to an overlay file system layer in the backend. Now the standard format of a Docker file is instruction followed by its arguments. Now Docker supports a list of instructions for the Docker file which you can easily find online. I will cover these details in later sessions. For now, I will be using only the from and the run instructions to build our image. Here on my Linux system, I have already created a sample Docker file, which is basically just a text file named Dockerfile. Now a Docker file must start with the from keyword, which basically specifies our base image on which we will be adding our own layers. In this case, I will be using the CentOS 7 image that we just downloaded. The next instruction is to run these two shell commands that will create a file which says hello inside a directory named /test1. Now to create this image, let me save and close this file and execute the docker command docker image build -t to name and tag the image. So let me name it test image1 and then provide the path where it can find the Docker file. There you go, our image has been built. You can see that each instruction is executed step by step and an associated overlay layer will be created in the backend if not already exists. You can confirm that our image is created using the docker image ls command. Now if we take a peek inside our docker overlay backend directory, you can see that a new layer has been created for the image we just built. If you see the div directory inside this layer, you will find only the test1 directory which we instructed to be created, because each layer only has to store the difference from its underlying layer, just like what is shown in this diagram. Now here you can see a new file called lower, which actually contains the shortened name of the layer below it, which in our case is the CentOS 7 base image layer. The OverlayFS driver will use all these information to build the unified view at the end. Now remember that layers themselves have no notion of belonging to an image. They are merely a collection of files and directories. An image, however, stores the collation information of its layers, which you can see in the docker image inspect command with the image name, that is test image1, which shows the different overlay directories that are part of the image. Also, docker image history command with the image name will show you the layered instructions that went into building that image. Now let me create one more docker image called test image2 that contains 3 lines of instructions. We will use the same Dockerfile. The first 2 instructions will be the same. However, I will add a third instruction to create another directory called /test2. Let us build this image, docker image build -t, let me name it test image2. There you go. Note that something interesting has happened here, where it says using cache. Now Docker uses something known as a build cache or layer caching. This is to avoid making duplicate layers during build and to optimize the process of building Docker images. Docker layer caching mainly works on the copy, run and add commands. What this means is Docker stores a historical cache of previous images and compares the instructions with the new image during the build process to see if any of them is being built with the same exact instructions in the same sequence. If a match is found, Docker uses the existing layer instead of creating a new one. In our case, Docker uses the existing layers for the first 2 instructions, which is shared between both the images, and goes about creating a new layer for the third instruction. If we peek inside our overlay backend, we can see only one additional layer created that contains the test2 directory in its diff. The other 2 layers are shared between the images and are not recreated. Here is a diagrammatic representation for better understanding, where I have shown the first 2 layers shared between the images. This mechanism greatly optimizes our build process. Now this obviously has some drawbacks in cases where the output of the run instruction is not the same every time you execute it. For example, in case of a git pull where you need to pull a new code every time, Docker will treat the instruction as repetitive and will reuse the existing layer instead of creating a new one. Here is an example I created just to mimic such a scenario. In this Docker file, I have put 2 instructions. One to use the CentOS 7 base image and the second to create a file with some random text in it. Let me build the image named test image3. Now remember, the random text generator will generate unique random text every time it is executed. Hence, technically it should create new layers every time. So let us try and build another image with the same Docker file named test image4. As you can see, Docker treats the instructions to be repetitive and uses the cache information to reuse existing layer instead of creating a new one. Here is a diagrammatic representation of what was expected and what we got instead. Now there are ways to work around this problem. One of them is to use the no cache option, which will force Docker to not look up the build cache and to create new layers for each line of the build instructions. Now the design of Docker files plays a key role in using the full potential of the Docker build cache and also affects the overall optimization of your builds. As a thumb rule, repetitive instructions that produce similar layers must be placed at the beginning of all Dockerfile, and the non-repetitive ones should be placed at the end as much as possible. This ensures that there is an effective sharing of layers across images. Also remember, sequencing is important when you write Docker files, as Docker will recreate all layers after the first mismatch is detected. Now this session is not intended to be a Dockerfile tutorial, which we will cover in later sessions with good examples. The intent of this session was just to make you understand how the layered approach of overlay drivers help in optimizing Docker image builds. Now that we have completed building our Docker images, it is time that we launch containers from these images. Now in the previous session, I explained what Docker containers are from an OS perspective. That is, they are just processes running in an isolated runtime environment created using C groups and namespaces. Now to launch a container, Docker first creates this environment and then mounts the overlay layer, with the Docker image being the shared read-only layer at the bottom, plus an additional writable layer on top specific for each container. Any operation at the container level is only stored at the topmost writable layers for those containers. The container specific writable layer is lost once the container itself is deleted, so does the data in it. This diagram is a good representation of this, which shows two containers launched from the test image 2 which we had created earlier. Both share the same read-only image layers, which is then merged with a separate writable layer on top and mounted inside the containers. Now let us try this out on our Linux terminal. Similar to Docker image command, the CLI command to manage Docker containers is docker space container. Here the help shows all available actions. To launch a container, the simple command is docker container run. Now I will be launching the bash process inside the containers, which requires an interactive terminal. Hence I will put the option -it for interactive terminal. Then the image name, that is test image 2, and the process that I want to run. There you go. Let me now launch one more container of the same image in another tab. We have now launched two containers, which you can confirm from the docker container ls command. If I now move into my overlay directory, you can see the topmost container specific writable layers created for each container. You can identify them as they contain the merged directory. Currently these layers have empty diffs, as I have not stored anything inside my containers. There are also layer directories with a trailing init, which I failed to mention before. These are nothing but container specific read-only layers that are created to initialize some mandatory files and directories for each container, like the host file, host name, etc. Remember, till the time we launch the containers, these layers are nothing but individual directories stored on your native Linux file system. Only at the time of launching the containers, the overlay driver kicks in to create a unified merged view of these layers to be mounted inside the containers. Now if we peek inside the merged directory of one of the containers, you can find the merged view of all its underlying layers. Here you can see the accumulation of all the directories and files from the underlying layers, which includes the CentOS base image directories along with the test1 and test2 directories, similar to what we saw in this visualization. Now if I check the mount output and filter only for overlay, you can see that it is this merged directory that is mounted inside our containers with the file system type as overlay. Now any file operation done inside our containers will be limited to our topmost writable layer. Let me just create a test file inside one of my container. Now if I check the diff directory inside my writable layer, you can see the file is now available there. Now the last and most important concept that I wanted to show is the copy on write operation, which I mentioned many times before but didn't explain what it is. That is because I wanted to show you that in action rather than just giving a theoretical definition. Now, it has been already mentioned that all file operations at the container level is maintained at the topmost writable layers, and the containers cannot modify the underlying image read-only layers. This is to ensure that the changes performed inside a container is not propagated to other containers that share the same image. However, what if there is a situation where I need to update a file that is part of the underlying read-only layer? This is where the copy on write mechanism kicks in, where as soon as you try to modify a file or directory that is part of an underlying read-only layer, in this case, let us consider the file test1/file.txt. That file or directory is now copied to the topmost writable layer of the container so that the container now has a local copy of that file for its operations. In one of our container, let me try to modify the file /test1/file.txt that is part of the layer 2. Let me write hello Karthik and save and close the file. Now the copy on write operation must have taken place in the background, which is invisible to us users. This is evident because from other containers that we launch, the contents of the file is still the same and has not been updated even though they both share the same underlying image layers. Now, inside our backend overlay directories, if I check the writable layer of the container, you can see that a local copy /test1/file.txt has been made available. Now, as a thumb rule, you should design your Docker image layer in such a way that there should not be a situation where your containerized processes have to update or write to an underlying image layer. This is because copy on write operations on relatively larger files can be resource intensive and might impact performance. Now, it is important to note that writable container layers have the same lifetime as that of the containers and will be lost once the containers are deleted. Hence, they are rarely used as a means of storage. Most of the time you will see mounted persistent and non-persistent Docker data volumes that store data outside the containers using one or the other means, details about which we will cover in later sessions. However, understanding the Docker storage layer is a key part in getting familiar with the Docker internals and its functioning. Also, it will surely enhance your overall experience of using Docker. Now that is the end of this session, and I hope you all found it interesting and learned something new. If you liked the video, don't forget to like, share and subscribe. See you next time.